That seems pretty good. Hello, welcome to the start of our week 7. I think we have a few people out there today, so welcome. Thank you if you're able to be here for the live stream. That's always nice for me to have some live interaction. Hello, that one kid. Nice to see you. And if you're watching the video later, then hopefully you've had a good week. So I know this is a big week in this class because at the end of the week, the first project is due. I know that the language is new and that there are some elements of assembly language in the code that make it more challenging, but hopefully you're finding that just the basic algorithms, how do I store the data, how do I adjust counters, how do I get the flow of the program going so that a person can shop at my virtual store? Hopefully all that stuff is well within your wheelhouse. And then hopefully if you needed the practice, then you're getting the extra practice on a program like this that has a lot of good stuff in it, in my opinion. Because you have to do a fair amount of logic, you have to do looping, you have to do arithmetic, you have to have variables that manage data over time. For example, the counters of the items that are in stock. So it's got all of the basics other than sort of the high level organization like structs and classes. So anyway, probably you're either finding it easy or you're finding, I hope anyway, that there are things in there that you could use the practice on anyway. Okay, so I'm going to kind of look at our schedule and then I'll do sort of the normal look at week 6. And then before I get into any content, we'll go have a look at the second project and I'll just sort of offer some heads up types of things about that. So let me get into one of our sections. Okay, so this is week 7. Just going to make sure you can still see what I see. Okay, good. So this is the last piece. Some of you have already figured out how to use it, I think, but this is the last piece that's needed for the last required feature of the first project, which is the change making apparatus. So once we have div, then we can do the change making, but all of the other stuff we've covered up to this. So then you can kind of see what's coming up, and the stack, a lot of you may know what a stack is in computer science. This stack is the same kind of thing, but it is has a specific application in the x86 processor. Then we'll do bitwise logic, which for a lot of you will be new. You'll be familiar with what bitwise logic is, but you probably haven't done any applications of it. And then finally, I'm just sort of giving you a heads up about this. So this Tues complement, the week of October 24th, that's when we start dealing with signed integers, so positive and negative numbers. We will not deal with any possibility of negative numbers before the week of October 24th. So some of you are beginning to explore that space and think about the ranges of values and what it means, the range of an unsigned 8-bit integer, for example, versus a signed 8-bit integer. But we'll dig in hard on those things the week of October 24. Let me get the project up. Did I put project 2 in the agenda? Project 1. You guys are on project 1. Okay, so anyway, I will open project 1 and then I'm going to go just step through the module, hopefully efficiently, so we can see what's in store for this week. So this week is entirely about the div instruction. It's different from mul, obviously, but it has sort of the similar thought problem. So when you're doing 8-bit division, there is sort of a 16-bit problem associated with it. And we'll talk about that in detail. But anyway, div is not harder than mul, but it is different than mul, and it requires a different setup than mul. And then we'll also, before I let you go or stop providing discussion, we'll look at the for loop in HLA, which we haven't written one because we haven't needed one. But in this week's lab, you will have a for loop, so I want to make sure that I've explained how they're written in HLA and what's going on in them, so that when you get to the lab, that will be familiar to you. The lab is fairly short, and most of it's been written for you, really. But it is a place to sort of safely experiment with the div instruction. All right, so Emberwolf asks, how do you get change if we do not deal with any negative numbers? Yeah, so good, Druid. So you subtract from the amount entered and you div from there. You deal with change without negative numbers just like we do every day in the real world. So no one ever says you owe me, I owe you a negative 25 cents, right? So in reality, we never do change as negative numbers, ever, in the real world. Now, it may be that in your software you have relied on negative numbers to trigger the idea that you owe change, and that's a fine way to go about that algorithm. But yeah, as Druid points out in discussion, you'll have the amount they paid and the amount that they owe, and if the amount that they paid is greater than the amount that they owe, then you subtract what they owe from what they paid, and then you have the overpayment amount, and that is where you make your change from. So it's just a matter of structuring the algorithm to acknowledge that there won't be any negative numbers there. Okay. But it is true that in the real world, I don't think I ever see negative numbers come up when change making happens. But in the software, it might, if someone decided to craft the algorithm that way. Okay, so one bit of reading, because it's the one instruction. The div instruction, by the way, is much more difficult with signed integers than unsigned integers. Just a heads up about that. We will be doing div when we get to signed integers, and it is much more difficult to understand, at least for most people. But for unsigned integers, div is not difficult as long as you remember the steps. Which is the big part of it, is just sort of remember the steps. Homework as always. The lab, I'll go ahead and pop that open as well, just to have that queued up. Discussion is a poll, which means that it's mostly a break for you all. Since you're working on the project this week, probably at least most of you. One person's turned it in, and I think maybe 3 or 4 people, from what I can tell, just in interacting with people, may have finished already. But anyway, it's just a poll, so you go vote in it, and it doesn't require research, and there's no commenting required. It's still just to keep us in the habit that every week we do a discussion, but you'll find the discussion is a break this week. And then finally, a reminder, so homework, lab, and discussion as always, and then also individual project 1, which is due October 9th. And somehow I need to get it off of that. How do I get it off? I don't want that. Yeah, see, it does that. I just hate this system. I really do. That's fine. Okay, so that's due October 9th, which is this Sunday. So all of the regular work plus the project, although we've had technically 7 weeks to work on the project. So hopefully you managed your time effectively over those 7 weeks and you don't find yourself getting overwhelmed, or you've left yourself a big swath of time this weekend. Okay, so let's switch gears. And I thought I wasn't going to do lab demos this week, but there were some people who put the extra work in, and I feel like I should acknowledge when people put the extra work in on labs. So let me switch over to my virtual machine and run a few demos from this week. Let's see, what do I need? I need a terminal, and then I need is there a test file, or what do we call it? Test. Okay, so okay, so let me fire up a few demos. Did I switch the view so you can see? I did. Okay, thank goodness. These are in no particular order. I just kind of name them 1, 2, 3, 4.hla as I decide on them. Okay, so what was the big deal about this one? So the way I tested this, and I hope that you guys did something similar, it takes several runs of it to test it properly. So you should give it just a normal run. So this one has, let me stretch this out so that maybe their text is not messed up. Okay. So typically I would try them all wrong and right, the difference. So try that one right. The product. And then I also did some, I'm not going to do the whole round, but in theory, if you're testing code like this, you need to test it for all of the eventualities. So overflow add, overflow sub, overflow mul, not overflow add, but get the right answer and the wrong answer, not overflow sub, get the right answer and the wrong answer, not overflow mul, get the right answer and the wrong answer. Hopefully you are doing that because you've only got one person's code to test that way, which is your own. I have to do the better part of 50 of them, which is my job, but I'm just saying that because you should take the time to do it if you don't take the time to do it. But as far as I can tell, everyone probably is because almost everybody's code worked perfectly. Let me get a couple more right. Get that one wrong, a mul error. So what was interesting about this one is that it was actually keeping a tally of what was going on while the program was running. So I played through the entire sequence twice. I got 3 problems correct. That's true. So anyway, that was just kind of, and then also this person pointed out, like, maybe you would show this one on Tuesday since I did the extra work. So I did. And also it was just kind of cool to keep that extra tally as it was going, which doesn't take a whole lot of extra effort, but I wanted to acknowledge that this person did take the time to do that extra bit of work to show that stuff. All right, so now I'll be quicker about this. So this one is just interesting. So some people had you enter new numbers in every section, and that's fine, or just enter the 2 numbers once at the top, and that's fine as well. Yeah, either way was fine by me. So this one I just thought was nice because they put little headings for the sections, and they took that little bit of time it would take to just separate out the different sections from each other. So that was a nice touch. This one is doing the clearing screen. Let me get one wrong. Get another one right. So anyway, this one is just nice because this person went and kind of strategically placed some screen clearing stuff, which just made the resultant program look that much nicer. So I appreciate the extra effort like that because I have to look at a lot of these, and looking at the ones that are slightly prettier is nice for me. And this one is sort of has used outputs to kind of label what the purpose of the lab is, which I thought was a cool touch. Also, this person kind of manually wrapped this line and did a spacing over for the second line. Nice touch there as well. Okay, so this one just has a nice interface to it with headings, and things are nicely formatted and separated. I'm just going to get it wrong on purpose. Okay, anyway, so nice ones. Those are just, I want just like to show a few and let you know that I do appreciate the work that you do. That bit of extra work that makes my life just a little bit nicer. Let me close these and I'll kind of reset this whole thing in just a bit. All right, so good job on those. That was cool. Oh, screen clear. All right, so Ember Wolf asked, how do you do a screen clear? So in HLA, the way you do a screen clear, oops. Yeah, so Druid has it in chat, and I'll go ahead and put it here on the screen so that people who aren't here for the live stream can see this part. So week 7. So thank you, Druid Dread, for Ember for the question, and Druid Dread for the answer in chat. So there is a library routine in HLA to clear the screen, and it is console.cls. I think that many of my labs have actually had this in them somewhere at the beginning, kind of. But anyway, that's just kind of to separate it out so it shows very easily. So that'll clear the screen wherever you are in the code. Of course, you have to be careful about clearing the screen because you don't want to clear the screen and wipe information off the screen before your user has a chance to view it. So typically you make sure that the screen is cleared after you have the user read what's on the screen and then provide some kind of input to move on to the next thing. So yeah, there's the clear screen. So good question, and thank you for the answer. Okay, so now, sorry, I got to switch views, and for some reason lost the browser. Still lost the browser. This is interesting. Well, I don't know where the browser would be. Yeah, very strange. Oh, maybe because I minimized it. Hold on, I'm fighting a little battle here with my streaming software because I cannot get the stupid browser back on the screen. Sorry, one moment. Something funny's been going on here. I do not see the browser in the options. Okay, weird. I'm just going to throw it out and do a brand new one. Okay, there it is. Sorry, everybody. Give me a sec. For some reason, the browser fell off of my display that you can see. Weird. And then I need to move it. There we go. Goodness. Sorry about that. Okay, so now we're back. Okay, so question in chat. If I was able to figure out change with the negative number, is that okay for project? Yes. If you can meet the requirement of the change with signed integers, you can certainly do that. I am warning you that is harder. Doing div with signed numbers is harder than with unsigned numbers, and I will not have talked about it, and I won't support it. So you're welcome to do it, but not with my help, because it's harder, and I think I would just be encouraging you to open a can of worms on yourself. So I would not do it. Just because we won't have explored the means of dealing with signed numbers yet. So I highly don't recommend it, but the requirements, I don't believe prohibit it. So you can do it. You would just be on your own. But let's look at the requirements. So that sort of comes up next anyway. If you can make it work, that's fine. If you can make it work, that's fine. So anyway, this is a vending machine simulation or a convenience store simulation, however you want to picture it. I tried to be pretty clear about how I want the flow of the program to work. And that was in part just to make sure that we all stay kind of within the range of the things that I know we know how to do. We show a list of products. They show their inventory numbers. And so your display should update. Every time a person buys something, the menu of options should update itself and should show the counters going down. So that's what this is all talking about. And I will be looking for that, of course, because it's a way for me to evaluate whether or not your counters are working, is to see them working on the screen. So we ask the user what item do they want to buy. We should not let them buy sold out items. So this is something that I do tend to deduct points for, is if someone lets me pick a sold out item and then forces me to say I want 0 of it. That's just bad software. So you guys are advanced enough that you should not need to do that. You should use logic to just say, oh wait, I've detected that item sold out, pick something else. So payment, so you should allow underpayment, exact payment, and overpayment, and deal with all of those things. So if they pay too little, ask them to pay more until they've paid enough. If they pay too much, give them change. And then this is a little bit artificial, I know, but I wanted to make a requirement that you have to use the div instruction in the program somewhere. So we're talking about credits because we don't have like 1.25 as a price for an item, or so the item would be 125 credits. And I used to just say in this assignment, just make it be, it costs 125 pennies, but that seemed to confuse people. So I call it credits, but then we do this artificial thing at the end where we take what credits we owe them in change and we produce sort of standard coinage change for it. So for example, if I owe them 41 credits and change at the end, they're going to get 1 quarter, 1 dime, 1 nickel, and 1 penny as change. So to me, that's a little bit artificial, but that seems to be the way that most people understand it better if I talk about credits, but still do this kind of conversion to standard US coinage at the end. Of course, the stock counter should go down. You shouldn't be able to select a sold out item, or at least the sold out item, if they select it, should say that item is sold out. And then there needs to be an exit option. So your menu should have an exit option. Your menu shouldn't force them to buy something to be able to check out. They should be able to exit. In fact, they should be able to exit before they bought anything. They might come into your store and decide, I don't like anything that I see, in theory, right, in a simulation, and be allowed to leave and not be forced through a purchase sequence to do that. One thing I can recommend, and I don't know if how many of you have this, but if you have a person, best if it's not a programmer, but just some other person who is not working on the same project, who can sit down and run your program, and then you can kind of quickly learn what does and doesn't make sense. It takes practice to do a user interface that directs the user the right way. So if you have someone that you can turn to and say, hey, would you sit down and run my program and tell me what doesn't make sense to you, that can help you improve your user interface. Okay, so anyway, that's just sort of high-level description. Please review the requirements carefully. Please. It's just a lot. It happens way too much that someone has a really, really good program, except for they didn't do one part, and then they're upset with me because they're deducted points for a feature they don't have, even though it doesn't seem fair that I would, it seems like I should apply the requirements the same to everybody. So just heads up about that. So documentation, that's easy because it's that stuff at the top. It's always required, and that's an easy 25 points. The output needs to look good. I don't care about the source code because of the translation problem through Canvas, so we don't worry about that. Needs to compile and run, of course, but it's the output is really where I can tell the amount of effort. 5 products. You can do more products if you want. There's no reason to, but if you find that you're kind of enjoying your theme and you want more products, then you're welcome to do that. I'm looking for a minimum of 5. A dynamic display. That means that when I select an item and I have purchased that item, the menu, I should return to the menu at some point, and it should show me the stock numbers having gone down for the item or items that I have purchased. And it should keep doing that over time. So proper management of the inventory counters means a couple of things. The main thing it means is that I shouldn't be able to purchase things after an item is sold out. You have to be careful about this because you don't have negative numbers, right? So you have to make sure that your logic is accounting for the fact that we only use unsigned integers. The other place where the counters can affect negatively your calculations is if you're using them to compute a total at the end. So some people in this program will have a person buy an item, pay for an item, give them change if required, and then re-show the menu of items, and then they buy another item, they pay for the item, and then they are shown the menu again. Some people will do it more like a shopping cart where I buy an item and it goes in my cart, and I buy another item, it goes in my cart. And then eventually I say I'm ready to check out, and then I'm given my total that I owe, and then I have to pay an adequate amount against that total. You can handle that however you want. So payment handling. So that means you must handle underpayment, meaning you need to make them pay more. You must handle exact payment, which means that they would pay exactly what they owe. There'd be no change and no prompt for more payment. And handle overpayment, which would be that you calculate change due. And I will test all of those things. So the way we're going to do it, and you may end up with dollar amounts depending on the amount of credits. So for us, it's going to be credits because I found that that's a way to communicate to people that we don't do currency yet. In fact, we never in this class do floating point numbers until the last day of the semester. So $1 would be 100 credits worth of change, right? And a quarter would be 25 credits worth of change. So we're doing this conversion at the end. If your items are all, well, no, you should handle all, because maybe I'll overpay by a lot just to see if I get the proper change all the way down from dollars. And then finally, a receipt at the end. So it should show me, so if you are doing one item at a time, you still have to do the receipt. So when the person says, I'm done shopping, I'm ready to exit the program, now they should see a tally, a receipt of all of their activities. Should show the quantities of all of the items that they purchased, the total amount that they, the price per item, the total cost of all purchased. I'll show you in my screen captures, but whether or not you're doing the shopping cart version or the vending machine version, there still needs to be a receipt that tallies the totals at the end of the program. All right, so here's mine. I have the minimum 5 items required. They are priced as credits or pennies if you want to think of it that way. And then notice that I have a variety of different starting stock levels, and that's because I want to make it easy to sell out items for testing purposes. And I would appreciate it if you implemented that and then left it that way for me. So if you make all of your items have 100 in it, that just makes life harder for you and me in terms of testing how it works to sell something out. So when I implemented mine, I made it easy for myself to sell out soda really quickly so that I could get to testing that really quickly. Okay, so you'll notice then the sequence of mine, they select a number 2, which is a soda. And then I say you purchased a soda, so mine is a shopping cart style. Press enter to continue. Then we get the menu back. The soda shows that the counter has gone down to 0. If I select soda again, I'm told that's sold out. Press enter to continue. And then at some point in here, I said I'm ready to check out, and now the payment part. So that I did it shopping cart style. So I kept track of how much total they owe, or I computed it somewhere. So there's my total. This is how much they still owe. So they put in too little. That's underpayment. So I tell them you still owe me 100, and now I overpay. And then I'm shown my receipt, my grand total, the change that I owe them, and then the change broken down into US currency style. So anyway, there's mine. And those screen captures that are there are not to dictate to you how you do your user interface. It's just for people who struggle to imagine how the flow of this program might be when it's running. I offered those screenshots. But you do your user interface however you want. Just remember that somebody other than you has to use it eventually. So you want to try to design it so that it is easy for them to see all of your functionality and test all of your functionality at the same time. Okay, so there's project 2. Please review the requirements. If you have questions or doubts about the requirements, Canvas Inbox, Piazza, office hours, and we will clear up whatever questions you have about the requirements. Okay, so that is project 2. What else do I have going on? Oh, project 1. I don't know why I keep saying project 2. I guess it's because all of my other classes are now working on their second projects at this point. Project 1 for you guys. Project 1. Okay, I am going to switch views now and talk about the... No, before I do that, let's go look at this documentation. So this Felix Cloutier guy and his documentation for the div instruction. This is pretty much what you're going to see in the HLA materials as well. Since we've been reading this person's documentation, I thought we'd come back and read it and see if there's anything to learn about it. I am most interested in the description. So notice there's something weird going on here, and it's similar to multiplication in that 8 bits of division work yields 16 bits of results, except for the 16 bits of results are actually very, very useful in and of themselves. It's a beautiful thing, actually. It's actually better than high-level languages typically do this. Now, I'll talk about what I mean, but notice something funny is going on here with the dx colon ax. We've seen that before. Edx colon eax, we've seen that before in the context of mul. The R, by the way, that's 64-bit Intel. We don't do 64-bit in this class. We do 32-bit. So anyway, just note something also kind of weird going on here with division. Somewhat like mul in the way that the weirdness is configured. Okay, so it divides a value in those registers by a source operand and stores the result. So notice when it says stores the result, so for 8 bits, you actually get 2 results. One of the results is in AH, and then the other result is in AL. Of course, that AH-AL combo is accessed as either AX or AH and AL separately. 16-bit divisions, we get 2 results, one of them in DX, the other one in AX. 32-bit divisions, we get 2 results, one in EDX and the other in EAX. The source operand can be a general purpose register or a memory location. And I'm pretty sure that if we look at the HLA documentation, we'll get the ability to do constants as well. All right, we're not going to worry about the 64-bit stuff. Non-integral results are truncated towards 0. We'll see what that means in a moment. The remainder is always less than the divisor in magnitude. That's not that big deal to us. We don't expect overflow to happen because there's kind of no way to divide a legal 8-bit by a legal 8-bit and get something that's not 8 bits. But there is this thing to worry about, which is a divide error, which for us will be when we try to divide by 0. So we will experiment with that and see what happens when we try to divide by 0. But other than dividing by 0, we don't have any carry or overflow situations to worry about with division because we're always getting something smaller out or the same size as what it started. We don't care about the 64-bit mode stuff. Okay, this table is useful. So if we are doing 8-bit operands, divide an 8-bit number by another 8-bit number, notice that we get 2 results for one division. This is one of the coolest things. It's rare in our line of work that you get something for free. What you get for free when you divide 2 numbers in x86 is you get a quotient, and at the same time you also get the remainder all at once. So if you are interested in the remainder of dividing one 8-bit by another, you simply check AH and that gives you the remainder. If you're interested in the quotient, the whole number part, then you check AL. Same goes for 16-bit things. We'll get, if we divide a 16-bit by a 16-bit, we get 2 results. We get a quotient in AX and a remainder in DX for free. We check one or both parts depending on our needs. Same goes for 32-bit stuff. We get a quotient in EAX and a remainder in EDX for free, which is pretty cool. So someone asked, I think it was maybe in the last week or two, like, is there a mod operation? On the x86 processor, there is not. You do mod by doing div and checking the remainder part of the result. Now, what I should have done, and I'm going to go do it, is let's go look at the HLA way of presenting this stuff together. Let me go back. I would put these buttons at the top, by the way, but I guess maybe they want you to scroll down and have seen the whole screen or something. Okay, so let's look at div. Here's div. We're not worried about idiv. That is for signed division, so we're not doing idiv for another few weeks. Okay, so we have a variety of divs. We're going to use this style of div, I think. I guess we don't have to, but yeah, I think that we will. It looks very similar to mul, but you just have to remember that mul needs the extra space because the result might be too big. Div needs the extra space because it's giving you 2 pieces of information, a remainder and a quotient. So we can divide with registers. We can divide with memory. That's variables. We can divide with constants. That's a relief to know that. So we can notice there is one thing that never changes, though. 8-bit division has to target AX, just like mul. 16-bit division has to target DX:AX. That cannot change. It's hardwired. 32-bit division has to target EDX:EAX. That's hardwired. It cannot change. Just like mul, div is hardwired. Has its results hardwired to specific parts of specific registers, so we cannot alter that. But we can divide by a register, divide by a memory location, or divide by a constant, and that's really all we need to know to feel good about the work that we're about to do. So now let's go play with it a little bit at least. Switch views. Okay, so I'm going to go ahead and leave my clear screen in there just to prove that it works. So there are extra steps. And let's give ourselves a variable or two to work with. So I'll just say x, which will be an uns 8. Leave it 0 for now. So let's just do some easy stuff. I guess we can do a y if we want. Do I want a y? No, I'm not going to mess with the y. Okay, so let's do some 8-bit div. 8-bit div. So the setup has an extra step. I have it on my agenda there. So we just mentioned that you get the quotient and the remainder all at once for free using div on x86, which is a great thing. So if we need the remainder, we run a div. If we need the quotient, we run a div. If we need the quotient and the remainder, we run a div. If we need the remainder, we check a different part from if we need the quotient part. Okay, and then I also put a note in there that setting up the numerator requires 2 steps. So let's give x a value. Let's just give it the value 10. Okay, so how do we set up to do division? We're going to set up the numerator first. So we're going to say the problem we want to do is, what is 10 divided by 3? Let's say x is currently 10. So what is x divided by 3? How do we solve that problem? 10 divided by 3. So we set up the numerator first. So we're going to move x into AL. Step 1 is to move x into AL. Step 2 is to move 0 into AH. We don't really need to understand this process, but basically, this will make more sense actually when we do signed integers. So if I'm doing 8-bit division, I have to understand that the result needs all of AX, AH, and AL. And to set up for this, you actually have to put your numerator component in AL, and then you do what's called 0 extending AH. All that really means is zeroing out all of AH. But if you put a value in AL and then you make AH be all zeros, then effectively AX is still the same value as your numerator, if that makes sense. And that's important because of the way the circuitry does division on the x86. It needs the whole 16 bits to be the correct value as a numerator. So Druid asks, is the second step required for 16? Yes, so the second step is required for 8-bit division, 16-bit division, and 32-bit division. You always have to do the second step for division. And it's also true, by the way, for doing signed division. It's just harder to do for signed division, or at least harder to understand. So yes, you basically have to set up, for 8-bit division, you need to set up a 16-bit numerator. And you do that by putting your value in AL, zeroing out AH, so that the numerator, being AX, is itself a correct value. So if you think about it, I'll do let me get the calculator. So if we're doing 8-bit division, let's just say I want to do 99 divided by something. So 99 fits in AL, these first 8 bits down here. But for the division to perform correctly, we need these entire 16 bits to be 99, but as 16 bits. And the way we achieve that is we put our 99 in AL, and then we zero out AH. It's important. I mean, I guess there's other ways to do this, but get in the habit of doing it this way, and you'll thank yourself when we do signed division. So we load up AL with the numerator value. We 0 extend AH so that now AX is, as a whole unit, the same value as the numerator value should be, which is just kind of hard to get accustomed to. 2 steps. You got to get a value in the numerator, and then you got to 0 extend it so that you have basically the proper setup. Then we can run the div. So we will div. So we're kind of saying here that AL equals AL divided by 3 is kind of how that works. AH is remainder, AL is quotient. But remember, the combo of AHAL is actually just written as AX in x86 assembly. So now the division is done, and now we can look at our results. So I'm going to lazily write it this way, by the way. Oh, I don't have to lazily do it. X divided by 3 equals, and then we will typecast to get the UNS 8. So there's the quotient. And then now let's do the remainder, which we will write as mod, and hopefully everyone knows that operator. Type UNS 8AH. So there is our result. So this is the quotient. This is the remainder, but notice I don't have to do the div twice. I do the div once, and I get both parts for free. Now, what I expect to see for a quotient here is 3, and what I expect to see for a remainder is 1 for 10 divided by 3. So that is, in fact, what we got. So div isn't hard. But you have to remember to do 2 steps of setup. With mul, you have to remember to do 1 step of setup. And if in doubt, by the way, do the setup over again. If you have any doubt, repeat the setup. There were a few people on the week 6 lab who forgot to repeat the setup in places, and it screwed up their math. So if you're at all in doubt, repeat the setup. And what do I mean by that for div? I mean, you put your numerator in AL, you 0 extend AH, and then you run the div against AX. That's for 8-bit division. Let's give ourselves a bigger one. So, oh, I should have called that X8. Why didn't I? Let me fix that. Okay, so let's give ourselves a 16-bit one and try the same thing. So X16, that'll be an UN16, and let's make that equal to 99. So let's do a what is X16 divided by 25. So it's still a 2-step setup, and then you just have to remember what size you started with and where you're going. So if I'm doing 16-bit operands, I need 32 bits of results. So we'll do the setup. So this time we put the numerator value into AX. We 0 extend DX. Why? Because of what's coming up next. So my fingers are gone a little bit astray. So this is like mul. When you do 16-bit division, it is hardwired to DX:AX. Hardwired. You cannot change this. There is nothing you can do about it. As bad as you might want to use EAX or EBX, because you know those have 32 bits, you can't. You're not allowed. It's hardwired. So this is how you have to do this division. And because you have to do your division into a DX:AX remainder quotient result, you have to 0 extend into DX. So that's why we're 0 extending DX, is because we are hardwired to DX as a remainder. Have to. So yeah, Amber Wolf asks, can we 0 extend the whole register and then move into AX? You can't, unfortunately. It's a good question, but there's no way to avoid this step because you are 0 extending into a different register. I wrote DX:AX because I am required to, because that is how x86 works. I'll switch the view back and show you. So in the HLA documentation, notice Here's an example. In fact, here's both of those if I can get them highlighted. You have no choice in the matter. You have to do it this way. It is hardwired into the circuitry. There is no way to not do it this way. So I am being told that's the 32 bits, which means that I put my numerator value in AX and I zero extend to DX. You're going to see me repeat that when I do 32-bit division. If I switch over to Felix Cloutier, by the way, notice that this is not even tainted with HLA. This is pure x86 assembly. Here's the AX for 8-bit. And notice that it is telling you AL is quotient, AH is remainder. Why? Because it's hardwired that way. You have no choice in the matter. DX AX. AX is the quotient, DX is the remainder. It's hardwired. You have no choice in the matter. And then finally, EDX EAX. EX is the quotient, EDX is the remainder. It's hardwired that way. So we have absolutely no choice in the matter. We just have to learn to follow these rules. Otherwise, we can't do division. But I'm glad that you asked, because I think the more times that we stop and think on that and say that to each other, then the more likely we will be to remember when we struggle with division, because it's weird. Yeah, so Druid has a good way to try to help you remember, is that your numerator always has to be twice the number of bits as what you're dividing. So if you're dividing 8-bit values, you have to have 16 bits of result, because you get two 8-bit results, an 8-bit remainder and an 8-bit quotient, hardwired to AX for 8 bits. So in the 8-bit section, the reason why I zero extend AH is because I have to. If I don't do this, it won't work, or at least it's not guaranteed to work. Has to be AH. In the 16-bit section, why am I zero extending DX? Because I have to. I have to. It is not guaranteed to work if I don't. And there's nothing I can do to change it. It is hardwired into my processor that way. So, but you know, we like to stop and kind of repeat this a whole bunch of times. So I'm glad that the question's being asked, so that so that I'm reminded that I do need to repeat it, because it's weird and it can be confusing. But it's a hardwired rule. You have to follow it if you want to do division on an x86 processor. Okay. So when we get done with all that, we'll get two results. We will have x16 divided by 25 equals, and then we will typecast to un16s. The AX part, that's the quotient. And again, the quotient is in AX for 16-bit division, because that's where it has to be. You can't move it. You have no choice in the matter. So multiplication and division are much less flexible and much less forgiving than addition and subtraction. DX is the remainder. You have to do this extra zero extending step. You have to. If you don't, you will not get correct results, at least not much of the time. You will be lucky if you do. Okay, so 99 divided by 25 should be 3 with a remainder of 24, I think. Yeah, right? So those are correct results, 3 and a remainder. Oh, I should have made it be a mod symbol, so that we are reminded that that is a remainder, even though I know I didn't have to do a mod. So there's a question about the moves. So I'll go back and I'll go over what the moves are doing. So for the 8-bit section, I have to move my numerator to AL. I have to if I want to do a division. So if I want to know what is x8 divided by 3, then I have to put the value of x8 in AL. I have to, because div won't work otherwise. So that's why I did that move, is because I need to copy that value into AL to set up for the division problem. I zero extend AH because I have to. And then I div around AX because I have to. That's what you have to do to divide one 8-bit by another 8-bit number. Okay, so good. No, but I'm glad you're asking, Emberwolf, because even if you think that you've locked onto it, it's okay to ask and force me to not gloss over this too quickly for people. So I appreciate it. I haven't done a move 0 to EAX yet, so yeah, so same thing. X16 is a 16-bit value. If I want to know what is X16 divided by 25, then I have to put that value in AX. I have to if I want to know the answer to this question. 16-bit division, the numerator value goes into AX because it has to. I 0 extend into DX because I have to. If I want to know the answer to this question, what is X16 divided by 25? And then I div into DXAX because I have to. I have no choice in the matter if I want to know the answer to this question. That is simply the way that, in that case, 16-bit division is done on the x86 processor. It is hardwired to work that way. All right, so let me give myself an x32. Doesn't really matter. Let's go for some big number, and then we'll find out stuff about it. Okay, so 32-bit division. It's the same process, but different registers, because now we're going 32-bit operands. 32-bit divided by 32-bit means 64-bit result. So the setup, I'm going to move. So here, the scenario is, what is x32, which is the value 3131, divided by, I don't know, 75, let's say, or 99. Who knows? So that's our scenario anyway, is what is that? If I were to compute it, use the computer to compute it. So I have to put the numerator value into EAX. I have to. That is where it must go to do 32-bit division on an x86 processor. Now I have to 0 extend something, which for 32-bit division is EDX, because I have to, because that's the way it is hardwired to work. So Druid asked an interesting question, which is, would this div work with floating point numbers? And the answer is no. Floating point numbers actually have their own registers and their own instructions that are completely separate from all the integer stuff. So the last week of the semester, we'll actually have a look at how floating point works. But it's a good question. So no, div, you can't do it with floating point. It won't work. There's actually special instructions that are that were engineered specifically to handle the floating point arithmetic problems. So they are their own complete set of instructions. The move is different, the add is different, the subtract is different, handling error flags is different. Floating point is its own separate kind of unit on the processor that has separate everything. It's quite interesting to deal with, and we will do it in the last week of the semester just so you've seen how it works. Okay. So 32-bit division. We move our 32-bit numerator value into EAX because we must. We 0 extend EDX because we must. And then we run our division. This time we're dividing 99 into EDX EAX. Why? Because we must. That is how it works. We have no choice in the matter. But what we get is a remainder in EDX and a quotient in EAX. So then we can go print those out. I don't know what these answers are going to be. X16, X32 rather, divided by 99 equals, there's the quotient. Mod, even though we know we don't use a mod instruction. that is basically what we get, and we'll use the mod just to remind ourselves. So notice the setups are all the same. You just have to remember where you're headed. So with 8-bit, you're headed toward AX, which is really AH and AL. With 16-bit, you're headed toward DXAX, and with 32-bit, you're headed towards EDXEAX. Unfortunately, there's no trick to just kind of internalize this logically. It's just a hard and fast rule that you have to learn, or you have to make notes for yourself so that you follow the rules. Otherwise, you'll get errors. So 99, that constant is anything that would fit there, right? So would 99 fit in 32 bits? It would, yes. So in this context, the compiler is going to treat that like a 32-bit value. Even though it doesn't need all 32 bits to represent itself, there'll be a bunch of zeros in there. It'll still be a 32-bit value. So if you place a constant in there, it will be adjusted to fit the space correctly for you. So this 99 in this context is 99 represented in 32 bits. And that's simply because of the target of the operation, which is 32-bit numerator and denominator. Now, I don't know what the result's going to be for those, so we'll just trust that those are probably correct. I could use the calculator to confirm it. Yeah, I'm feeling pretty confident about that, although let's do it. 131 divided by 99. Is 31 and some change. So there's the 31 and no doubt the change. So 31 times 99. Yep, so 3131 minus 3069 should be 62. All right, so there's confirmation that our math is in fact working. So yeah, this can be confusing. I'm hoping I will just leave these basic setups here to remind you. So if you are in doubt, do the entire setup. Don't leave it to doubt. Put your value in the appropriate place. 0 extend the appropriate place. Run the div. And then remember what you get after the div is you get 2 answers, a remainder and a quotient. And you cannot, but let's just see what happens if I decide I'm going to be clever. So let's just see what happens if I were to, for example, say, let's just use the x8 again. So x8, which is 10, 10 divided by 9, divided by 4, I don't know, whatever. But let's just see what happens if we were to try to relocate some things. So let's just say I get the whole 8 to 16-bit things. But what if I want it to be in DL instead? Can I do that? I cannot. So line 49. Unfortunately, the error doesn't say anything about, hey, you can't just make stuff up around div, which would be nice if it did. So I'm running this error just to show you that if you, so line 49 is a div, and if I get any kind of error on a line that has a div instruction on it, then I need to go back and review the entire process and make sure that I am respecting all of the stuff that I'm supposed to respect. So can I target a division into DL? I cannot. For 8 bits, the target is AX, which is AH and AL, so value goes into AL. The 0 extending goes to AH. The target is AX. Has to be that way. So the compiler errors are not helpful here. So just heads up about that. Let me put it back. You cannot change these targets. Okay, so there's one. Let's try to divide by 0 just to see how that would work. So we'll do a correct setup. And let's just see what happens if we try to divide by 0. So x8 to AL has to be, 0 extend AH has to be. But now I'm going to try to divide that by 0, and I'm going to see what happens. It ran, or at least it compiled. Let's see what happens when I run it. Okay, so crash. The program crashes the HLA exception at line 170, which is not helpful, by the way. So I'm showing you this again, just to sort of heads up. If I'm doing division instructions and I get some kind of exception pop out, check for the obvious things like divide by 0 kind of stuff. So note that I got an exception, and I will just try this and note exception. So you can't divide by 0. It's illegal on the x86 processor. It throws an exception, which is what we're seeing reflected out to us by HLA. Okay, so that's all the basic div stuff. Let me queue that up to be offered as a sample on the lecture page. Okay, so no, thank you very much for the questions about that. If in doubt, or if you just think maybe I should ask this question because someone might have it, then go ahead and ask, because the more times we repeat these things together, the better. Div is weird. Div with signed stuff is weirder. Heads up, in 3 weeks. This will seem like this was way easier in the old days of the unsigned integers when we get to the signed integers, and notice how weird div can be. Okay, so there are the division samples, and I'll post those on the lecture page. Yeah, so last thing is, let's do the, let's get the lab up, and we'll just see if there's anything odd about it. So I'm not showing you this, but I'm over there in my browser grabbing the lab code. Oh yeah, for loops. I forgot for loops. There's a for loop in here. That's going to make me go back and redo my sample code. So I'll be ready to do that. Okay, so hopefully you're still seeing. Okay, so this is the lab. There's a console clear screen in the lab. So what's going on in this lab? So some of these, I mean, it's kind of free points, but I also just sort of think that getting you, not letting your eyes stray away from some of these fundamental procedures, like how do you read input and where does it go? I'm just hoping that keeping your familiarity this way is useful to you. So that's why I'm asking you to implement a get number for yourself. But you know how to do that already. Go again, same thing, implement that. So that's 2 freebies. The loop has been written for you, so that's not really the concern, but I am going to do a sample so you can see what's going on here. You'll discover that it's pretty much the same thing as the for loops that you've written in the past. And it's telling you all the steps. So set up a numerator, do the 0 extend step, run the divide, check the remainder. So all the steps are there to remind you of the setup in this loop. And the rest of it is pretty straightforward. So this is a short lab. It gets you to focus mostly on this problem of practicing the setup to do unsigned division on a 16-bit value, which means you're going to have 32 bits of result. Okay, so that's the lab, but I need to tell you about this loop real quick. So let me put a loop down here. This thing I just inserted, by the way, is just a blank line. New line, so new LN, all small letters. That's just to put a blank line in the output. Okay, so let's do a quick for loop. So for loops are generally written in a couple of different ways, but Let's write a for loop to answer this question. What are the factors of x8? Ooh, let's do a more fun one. Of x32. This will be a more fun one. What are the factors of x32? So hopefully everyone knows what I'm talking about here. This is all of the values that evenly divide themselves into x32, whatever it happens to be. So the way I'm going to do that is I'm going to write a loop that basically goes from 1 all the way up to the value itself. So if x32 were 10, then I want to write a loop that goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm going to test every one of those values to see if it's evenly divides into x32. And I'm going to do it wrong first so that hopefully we can talk about what's wrong about it. So x32, that is my 32-bit unsigned variable. Okay, so I'm going to write a loop that goes from 1. And generally you can start at the reason why I'm using C here is because it's traditionally used as a counter. Why? Because it has the letter C in it. Because we humans are sometimes have no need to be clever. We're just like, well, which register should I use for a counter? How about the one with the C in it? So great. So we're writing a loop that's going to start at 1. So CL is our I. This is like saying int I equals 0, except we're using the register CL. We're going to take CL all the way up to, including x32. And then we're going to increment it 1 at a time. So I have already made a mistake. But generally you can start with the smallest value of the C register, the smallest section of it that will accommodate your values. So, well, let's just see what the error says, because the error is going to be the tell here. All right, so it says type mismatch around the less than or equal operator. So that is pretty darned obvious. So does someone in chat want to tell us all what's wrong with my for loops, my counter choice? CL is too small. So you are correct, Druid. CL is too small. And in fact, if we look at specifically at this part that is around the less than or equal to comparison, I'll put a space in there. Maybe that's easier to read. Oh, I don't like it that way, though. It just doesn't look right to me. If we look specifically about what's going on around this CL is less than or equal to x32, what's the mismatch? And what would be a match? CL is too small. It's 8 bits. x32 is 32 bits. ECX, good one, Druid. So this has to be ECX. Why? Because I can't compare a non-32-bit register with the 32-bit variable. So I have to have a 32-bit register, which means that I really just should be using the entire ECX as my counter in this case. So the choice of the size of your counter here, CL, CX, or ECX, is based on what size do you need to do the thing that you're doing. I'm really writing a counter that goes all the way up to x32, which is 32 bits, which means that the counter has to be 32 bits. So I just adjust the counter setup all the way across to be ECX for that reason. Yeah, so there's that. And again, the reason why I'm choosing ECX is not because it's required. You can use any register you want as long as it's the right size. But the C register is traditionally used when a counter is wanted. So that's what I do. It's what people expect in the world of assembly, but it's not required. Okay, so why am I doing this counter? Because I want to test it. So standard out to output. So I will be testing this ECX value. I'm going to go ahead and run it and make sure it gives me the right results. But this counter is going to be the values from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to whatever x32 is. That's going to be what I'm going to try to divide into x32 to see who yields a 0 remainder. So let's quickly check that. Did I save? I did save. All right, so there's my loop. It is too much for my terminal buffer to show, but it goes from 1 all the way up to 31, 31, and everything in between because it is being incremented one at a time. So x86 does have an increment instruction, which just adds 1. If you wanted to, you could write that as add 1 to ECX, and that would work the same. But I use increment ECX because I know what that means, and I think all of you know what that means. So, so start ECX at 1, and I equals 1. I less than or equal to x32 variable, I plus plus. That's what that loop's doing. And the reason why I'm doing this loop is because I want this ECX to be tested against my x32 value. Okay, so how do I test it? Well, I am dividing x32 out by stuff. I need to 0 extend EDX because I must. And then I'm going to divide ECX into it. So there's the math. Put the value in EAX, 0 extend EDX because I must. Run the div against EDX, EAX because I must. And now this will be my last question for chat, and then I think we're pretty much done for the day. Which register? So what result am I interested in here? So which register of EDX or EAX am I interested in, and what value is important? What value am I looking to find there that's important to me? So what I'm asking is ECX a factor of x32? Does it? So you're right, and it's EDX strictly. There we go. So Alu is right. It's the D register, and then Druid Dread actually wrote the logic in chat. So if EDX is 0, that means there was no remainder when I divided 3131 by ECX, which will be 3131 divided by 1, divided by 2, divided by 3, divided by 4. So that remainder part, if I get no remainder, then I have a factor. So I can say, I'll take the new line out right here, by the way. So if EDX is 1 after that division, then I can safely say, I need a space here. Type uns32 ECX is a factor. And then I'll spit out a new line no matter what the result. So that's what I'm doing in this little loop here is I want to see which of those ECXs as I march from 1 up to and including the value are the factors. What is it evenly divisible by? Do I need? This may be more output than we want. We'll fix it. Yeah, let's get rid of this part and only print out the factors. So anything that's not a factor, we're going to ignore. It's not prime because it has, it does have 1 in itself are factors, but then also way out there somewhere 31 and 101 are also factors of this number, meaning they divide evenly into it. So this is similar to what the lab is asking you to do, except for it's asking you to keep count of that as well. So that's where I'll stop. Thanks a lot for being here. Thanks a lot for the questions and the answers. And all of the contributions. I really, really appreciate it. Yes, so OI Hernandez is right. This is not optimized at all. So you are correct, OI Hernandez. If we were to stop at half the value or use the square root of a thing. There are other there are better algorithms. The reason why we're using this particular algorithm is not because we want to have a good factor finding algorithm, but because we want to force ourselves to practice div. So it is intentionally inefficient, but you are absolutely correct that this is a terrible algorithm for actually finding out what are prime numbers. That's true. But I think a decent algorithm for trying to give people an excuse to practice div and try to make sense of the remainder and quotient results. Okay, yeah, a good point. Okay, that's it for me for this week. Can you explain the logic of the factor counter? Sure, the logic of so a prime number has two factors, one in itself. That's the logic of it. If there are two and only two factors, and you checked everything from one all the way up to and including the number itself, and you get two factors, that's a prime number. Any non-prime has more than two factors if you're counting the number of factors. So that's sort of an application of that information. Right. Yes. So someone's asking factor count. That's right here in the lab on number 6. Increment the factor counter. So that's where that variable comes into play, is in this algorithm to show factors is also counting them. So we're printing out the factors as we discover them, and we're also keeping track of the count of them using that variable at the top. And then we're actually returning that value from the function. And then we are printing that return value in the main part of the loop. So that's where that variable, in fact, where is that? Oh, it's in the var. I see what you're asking. Yeah, so there's the counter that we're using. So this var is for local variable making in HLA. So that's what we would call an automatic local variable. It's only available to the procedure itself. So thank you. I missed the whole var thing. So the question is, this var factor count in the show factors procedure, what is it? It is a local variable, and that's how you do them in HLA. With the var keyword, which means automatic local to the procedure. Good question. I completely passed over that. And then its use is what I was saying before in number 6 and 7. All right, good question. Thanks. I missed that and forgot about it. Okay, that I think is with that I can say have a great day, have a great week. Canvas inbox, Piazza, office hours if you get stuck on any part of the project. Otherwise, I have a lot of them to grade, so I am of the fervent hope that everyone has a perfect, wonderful one, because that makes my grading life less depressing and faster, as it turns out. So that's always my fervent hope, is that everyone has a great run through the project. But if you do find yourself stuck on anything, use the normal channels to get in touch with me and or your classmates so that we can help you. Other than that, I will see you on Tuesday next week. So thank you, Druid. I appreciate it. Thanks for all the questions. Thanks for the feedback. Thanks for highlighting the things that I needed to stop and talk about a little bit. So always appreciate it. Have a great week. Have a good run. Have a great run through the project, I hope. And I will see you on Tuesday next week.